Imagine a massive toy castle made of tiny interlocking plastic bricks. Now take a giant mallet and smash it into dozens of flying pieces. If you were to sweep up the mess and sort it out, you'd find distinct piles. Even without seeing the original castle, spotting tiny wheels, long planks, and plastic flags gives you a pretty good idea of what was just destroyed. That logic of smashing something apart and sorting the leftovers is exactly how chemists identify unknown substances. They use a specialized tool for this called a mass spectrometer. Because a chemical molecule is roughly 1 billion times too small to hit with a physical hammer, this tool uses raw electricity and magnets to break apart the invisible structure and sort the pieces. The process starts by turning the chemical sample into a gas. This lets the individual molecules float freely into the starting chamber of the machine. Next comes the hammer. A glowing hot wire fires a high-energy beam of electrons straight into those floating gas molecules. The collision knocks a negative charge right off the molecule, leaving it positively charged. These broken, charged pieces, now called ions, are what the machine actually tracks as they shatter into fragments. Because these pieces are now carrying an electrical charge, the machine can use electricity to physically grab and steer them. Electrically charged metal plates act like magnets pulling on a paper clip, accelerating these positively charged fragments forward and shooting them through a narrow slit. In less than a second, a sitting puddle of chemicals is transformed into a high-speed stream of shattered, electrically charged molecular pieces. The speeding fragments now enter a vacuum tube that bends in a wide curve, passing right through a strong magnetic field. Picture rolling a heavy bowling ball and a light tennis ball forward at the same speed. A massive gust of crosswind hits them both. The heavy bowling ball's momentum pushes it straight through, while the light tennis ball gets blown way off course. Inside our machine, the magnetic field acts exactly like that crosswind. It pushes steadily against the speeding, electrically charged pieces as they fly by. The heaviest fragments barely budge, crashing into the outer wall. The lightest ones get blown too far and hit the inner wall. Only the fragments with the perfect balance of weight and electrical charge will stay on the track and make it around the curve. By fine-tuning the magnet, the operator controls the wind. This translates a microscopic difference in weight into a physical difference in distance, perfectly sorting the invisible pieces. At the very end of the track, the fragments that survive the curve strike a specialized detector. Because the magnet bent the heavy and light pieces at totally different angles, they hit the detector at different spots or at different times. The detector's job is simple. It acts like a digital toll booth, counting the impacts to figure out exactly how many fragments of each size made it through. A computer turns these counts into a mass spectrum chart. For ethylbenzene, it shows exactly which pieces hit the target. The horizontal axis shows the mass. The vertical height shows abundance. A taller spike means the detector caught more fragments at that weight. Every unique chemical shatters into its own highly predictable pattern. This diagram shows how a compound called neopentane always breaks into specific chunks weighing 57, 41, 29, and 27 units. That pattern acts as the chemical's fingerprint. By comparing these unique readouts to a library of known patterns, scientists can look at an unknown smudge of powder or a drop of liquid and instantly identify exactly what it is.